Hello everyone, my name is Yiwei from Carnegie Mellon University. Today I will present our work on probabilistic safety-assured adaptive merging control for autonomous vehicles. This work was completed with my colleague Wenhao and my advisor Dr. John Dolan. Here is our today's agenda with all the important questions we are going to answer. To begin with, let's look at what is our motivations. So it is a fact for the autonomous vehicles that they will have to share roads with human drivers before they completely replace all the human-driven cars in the near future. So our goal here is to provide a safe control method to help the ego vehicles to interact with human-driven cars safely, efficiently, under uncertainty. The scenario we're going to study here is the ramp merging scenario, which is one of the most important and typical one where the autonomous vehicles interact with human-driven car. And here is a simple illustration where the green car on the main road is the autonomous vehicles we are going to control, and the red car on the ramp is the human-driven car. The goal is to help the green car merge with the red car safely. The uniqueness about this scenario is that we need to balance the driving aggressiveness and conservativeness to make it applicable to everyday traffic situation. And now let's take a quick look of some of the related works, and then we'll define what are the technical objectives in this work. The current existing works on safe control can be generally categorized into learning-based method and control-based method. The learning-based method has the advantage of organizing the relationship among different variables in an explainable manner, and they can also handle the uncertainty well. However, they cannot provide theoretical guarantees on safety. And that's why we turn to the control-based method, specifically control barrier function-based method. The advantage of using control barrier function is that they can provide provably correct safety guarantee. However, we see that most of the existing works with control barrier function has a deterministic environment setting, and by using optimization-based controllers, potential conflicts among different constraints can cause a problem in feasibility. And here are our technical objectives for our work. First, we place safety as the priority as we seek the formally provable safety guarantee. And secondly, we want to remove the finite support uncertainty assumption that was made by some of the related works. And third, we want to provide solution feasibility guarantee in runtime. Here we're going to take a quick look at the background of control barrier function. We start by defining an admissible control space, and we say that any controller that belongs to this space will render the safe state set H forward invariant. In this work, we consider the pairwise vehicle safety function H, and here's how H is defined. This term represents the Euclidean distance between the pairwise vehicle, and the R safe here is a predefined parameter of the safety margin. So next, we will show how is our method constructed. And here's our system dynamics. In this work, we use double integrators to describe the vehicles, where x and v adaptation and velocity of each vehicle. U is the acceleration control input of the ego vehicle. We use epsilon here to represent the motion uncertainty. It is a random variable that follows Gaussian distribution. Here is our completed formulation as a bilevel optimization problem. The objective function here represents the control effort in a minimally invasive manner. The first constraint here we have is the kinematics constraint, the minimum and maximum allowed acceleration for the ego vehicle to take in. The second constraint we have is the safety constraint. We formulate it as a chance constraint problem, with eta on the right-hand side as the assigned confidence level for the statement inside the bracket, and the statement is simply the control barrier function statement. And the third constraint here we have is the problem feasibility constraint, and it is an optimization over the CBF parameter alpha. And you may wonder, where do we get the third constraint, the feasibility constraint, from? To answer that question, we first need to figure out when does an optimization problem become infeasible. And here's our safety constraint. We can actually reorganize it and write it in the form of AU less than or equal to B. And we use two ellipsoids here to represent the safety constraint and the kinematics constraint we have. And we see that the overlap of these two ellipsoids represent the feasible solution interval. And therefore, we can see that solution infeasibility happens when the overlap of the two intervals becomes empty. And from this reorganized safety constraint, we can actually derive an upper bound or a lower bound over control input U. And with the expression of A term and B term, these are state-dependent variables. And through observations, we can see that if we decrease the value of alpha, here's how the other terms is going to change. Okay, so here's how it looks when we visualize our observations. We have the red dashed lines here to represent the upper bound or the lower bound we derived earlier, and we have the blue intervals here to represent the reducing solution set while alpha keeps decreasing. And we can see that when a term is larger than 0 or equal to 0, the infeasibility is about to happen when the red dashed line overlaps with the minimum acceleration here. And when a term is negative, the infeasibility is about to happen when the red dashed line overlaps with maximum acceleration here. And here is how we come up with the proposed algorithm. This is a stepwise optimization. So basically at each step, we first optimize over control input U to provide the safety guarantee. And then we optimize over the CBF parameter alpha to provide solution feasibility guarantee at the next step. Here comes the experiment part. First, we would like to show that the proposed method is valid and efficient. We have our testing scenario as the Eagle vehicle versus a single merging vehicle. And this time we set our confidence level to be 99%. The objective of the validity test is to demonstrate the probabilistic safety over a large number of trials. The initial conditions of the Eagle vehicles are randomly generated, including the position, velocity, and strategy the Eagle vehicle takes. And we run the experiment for 400 times. And here is our result. We have the black dashed line here representing the predefined safety margin. And for all the 400 trials, they stay on top of this black dashed line and therefore keep safe. Hence, we achieved a 0% collision rate. So for efficiency test, the objective is to compare the performance of the proposed method with a traditional CBF with fixed parameter alpha. And we use two different optimization-based controllers on the Eagle vehicle for performance comparison. And the difference between the two controllers is with or without updated CBF parameter alpha. And here's the result for the efficiency test. We still have this black dashed line as the predefined safety margin. The blue line here represents the traditional CBF with fixed alpha value. And the yellow line here represents our proposed method with updated alpha. The green zone here represents the time interval where in our proposed method, the alpha value is getting updated, meaning the alpha is keep changing over this interval. And we can see that both methods share the same performance before they enter the green zone. And they start to differentiate since they enter the green zone. And for the traditional control barrier function without updating their alpha value, the optimization problem soon becomes infeasible. And after that, it breaks the safety requirement cause collision. And our methods keep the vehicle safe all the time. Hence, we say that our proposed method provides a dynamic solution feasibility guarantee in runtime. In the second part of the experiment, we are going to discuss about the factors that can affect Eagle vehicles' behavior generation. The first factor is, of course, the CBF parameter alpha. As we said, alpha represents the degree of driving conservativeness or aggressiveness. And objective here is to play with different value of alpha and observe the performance. Here we're looking at the case when the Eagle vehicle merges in the back of the merging vehicle. And we can see that the larger alpha is, the more aggressive the driving strategy is, and therefore the more quickly it gets close to the merging vehicle in the front. And here's the case when the Eagle vehicle merges in front of the merging vehicle. And we can see that smaller alpha is, the more conservative the driving strategy is, and therefore the more quickly it will escape from the merging vehicle in the back. The second factor we think can affect the Eagle vehicle's behavior generation is the initial conditions of the Eagle vehicle. And here we consider the merging task with two merging vehicles on the ramp. And we give two different initial conditions to Eagle vehicle in case 1 and case 2 and compare their performance. And here's our demo for case 1. We give the Eagle vehicle a closer initial location from the merging point here and a faster speed. And then we see that aggressive merging strategy here makes the Eagle vehicle merge in front of the first merging vehicle. And a conservative driving strategy makes the Eagle vehicle merges in between the two merging vehicles. Now let's see what will happen in case 2 if we drag the Eagle vehicle a bit further from the merging point and give it a slower speed this time. We're still using the same aggressive and conservative driving strategy, and we see that this time the aggressive driving strategy only makes it merge in between the two merging vehicles, and the conservative driving strategy makes it merges after the second merging vehicle. By comparing the case 1 and case 2, we can see if we keep the profile of both merging vehicle and driving strategy of the ego vehicle the same, changing the initial positions and velocity of the ego vehicle will also change its merging behavior. So in conclusion, in this work, we propose a bi-level optimization-based control framework to enable the autonomous vehicles to achieve consistent safe rank merging behavior under uncertainty with 0% collision rate. We also provide formally provable safety guarantee and solution feasibility guarantee in runtime. We also discuss the factors that can affect the ego vehicle's behavior generation. In the future, we plan to combine the proposed framework with learning-based methods that use real-world dataset to determine the appropriate driving strategy. With that, I would like to conclude here. Thank you for your listening.